Welcome back. Hopefully you watched part 1 of this video series about space-based laser communications, otherwise known as free space optical communications. This is an exciting new technology that should revolutionize the way we communicate and transfer data in space. Today I'll demonstrate 2 ways to use laser communication to provide worldwide data, voice, and internet connectivity. One method requires 2 or more laser communication relay satellites in geosynchronous equatorial orbits on opposite sides of Earth, as I now show in the image on my right. Each relay satellite has a constant view of nearly half of Earth, making it highly probable that at least one optical ground station with good weather can be seen. Remember that optical beams are highly attenuated by clouds, rain, snow, fog, dust, and smoke. Therefore, we cannot transmit from the relay satellites to ground if there is bad weather at the ground station. If 2 relay satellites are used, one on each side of Earth, one can always be seen by satellites in low Earth or medium Earth orbits. Of course, having more relay satellites is better, but the minimum is 2. Finally, due to the apparent stationary nature of these orbits relative to the ground, no complicated pointing and tracking is required for optical ground transceivers. A disadvantage of using this orbit for the relay satellites is the latency in data transfer because of long beam travel distances and the limited speed of light. There will be a 1/4 second delay before the information reaches the ground. LCRD was NASA's first space-based laser communications relay demonstration. This payload was hosted by the Space Test Program's Satellite 6 spacecraft and was launched on 7 December 2021. It flew in a geostationary orbit and completed its mission June 2024. I now show a NASA-generated image of this satellite. The satellite had 2 transceivers, or optical space terminals, on board, one for communicating with other satellites and one for communicating with ground terminals. A switching unit was used to route data between the 2. Operators used this mission to study different modulation and encoding techniques while perfecting tracking methods. NASA also used it to learn more about the effects of weather, wind, and atmospheric turbulence on laser communications. Data relay demonstrations were conducted between a laser terminal located on the International Space Station and an optical ground station. NASA is planning to build a permanent optical relay capability as part of the next generation relay architecture. This will provide NASA space experiments with high-rate transfers of data to ground. NASA isn't the only organization to see the advantages of using a geostationary orbit for relay satellites. The Japanese Aerospace Exploration Agency has placed one in a geostationary orbit. It's called the LUCAS, or Laser Utilizing Communication System. And the European Space Agency has 2. These are called the EDRS, or European Data Relay System. An alternative method for providing worldwide laser communications is to use a large constellation of low Earth orbiting satellites which communicate via intersatellite crosslinks, as I show in the image you now see. Using this method, data can be routed around the world from one satellite to another until a ground station with good weather is found. The advantage here is that latency is much lower due to the shorter distance traveled. The disadvantages are that it requires more satellites, and optical ground stations must track the satellite that it is currently communicating with. Based on information available on the web, Starlink uses this method for providing worldwide internet connectivity. Starlink plans to have 42,000 satellites in low Earth orbit and currently has over 9,000 operating satellites, most of which already have optical inter-satellite crosslinks. It's not clear to me that Starlink yet has any optical ground stations or gateways for connecting to the internet. Therefore, microwave ground stations are probably being used, and if so, this represents a significant bottleneck for data. So how do we accurately point from one spacecraft to another using a narrow laser beam? To do this, you must first accurately know where both spacecraft are in space. For example, to find the correct pointing angle from spacecraft B to spacecraft A, you must subtract the vector position of spacecraft B from the vector position of spacecraft A. The resulting pointing vector, vector C, is only as accurate as the original two vectors. I hope you found this video informative. If so, give it a like, watch our other videos, and spread the word about this channel. Also remember that we write free educational software for satellite orbit simulation and space mission design. To download this software for the Windows operating system, click on the link provided. Thanks for watching.